Hello. Um, Today I would like to try to show some use of the Irena tools to compare size distributions from various tools in a manner which was not really original designed in, and so there's going to be a few more Igor tricks which every user should probably learn because they're extremely useful. So basically, I want to compare different tools and show that they get sufficiently same results. There's going to be slight differences, but they'll be close enough. So, as I said, I want to document that we get similar enough results. And if you think about Irena packages which are available in Irena tools, um, we have three ways to obtain a size distribution of particles. The primary and most common one would be the modeling package, um, where you define a shape of a size distribution. So you say, I have a log normal size distribution, Gaussian size distribution, LSW, and there's one more. You define your form factor, sphere, rod, you give it a contrast, you give it other parameters potentially, give it a structure factor, and you can combine a number of other models. This could be other size distributions, they could be unified fits, whatever else. And you get 10 models together, so you can create quite a complicated model. So that's the one which is basically the primary one I consider for size distribution. The second one uh, The second one is an old and favorite of many, sizes or size distribution tool. This one is a free-flowing bin size distribution with three different optimization methods. For example, maximum entropy, regularization, or total non-negative least squares. Those are the three different methods we have. There are a few form factors like sphere, spheroid, rod. Most of the time, sphere is good enough. And some of the assumptions behind that, it basically assumes all particles have the same shape. So all are same sphere or same spheroid. They have different sizes, but same shape. And they all have the same contrast. So that's another one. And then we have a third one, which is kind of unusual. You can use unified fit. And if you do a unified fit and you can assume that your particles have, the first thing is that the unified level represents particles and they have approximately log normal size distribution. The unified fit can estimate and back calculate a size distribution based on these values of G, R, G, P, and B. The assumption behind that is that you have a spherical shape only, and there are some cases where it just fails because it seems there's too high polydispersity and it cannot calculate it. There's some interesting challenges which I discovered when I was playing with it before making this movie. Interesting is that modeling can use radii or diameter. Sizes always use diameters. There's no way to get radii out of it. On the other hand, unified fit always uses radii, and there is no way to get diameter out of it. And yes, there's a history and challenges and how the today about 20 years old code has grown. And so, yeah, life would be too easy if I just made a proper decision 20 years ago and stick with it. Anyway, so let's start with this. This was kind of fun when I was testing it. So first thing is, here is Igor. I'm going to load in. I just need an Irena, nothing else at this moment. And we'll compile. Now, first thing is we need to create some model data. And to do that, we can use modeling package. So you can just grab it. And here is my modeling package. Now, instead of having QSEX data or QRS data, I can actually select here that I have a model data. I want to do a model. And it gives me Qmin, Qmax. You can change those. I found out that it would be better to have maybe 300 points. You actually want to have a log Q stepping over this range of Qs. Keep in mind, there's a huge range of Qs. This is basically a USEX range of Qs. And then you just simply hit add data. What it does, it adds basically just a Q scale. The intensity is set to 0, and you have a beautiful Q scale here. I'm going to put in a background of 0.1. in there. That's useful because there's usually a background, and you're going to see that's actually useful in the future. Now, what I'm going to do next is I'm going to come in here and say I have a model, and you can see I have 10 populations. So I'm going to check one of them and ignore everything which is here. I'll leave 5 volume percent here. I'll set this one to maybe 20, and this one for maybe, let's try 90. And then we can do a calculate model. And this is actually not really scaled properly, but if we say auto scale axis, you're gonna see it. So what you see here is we have a Gini area, we have a power law slope, which because this is a smooth sphere, this is gonna be Q2 minus 4. Eventually we go to background of 0.1, so it doesn't go all the way to infinity, it just flattens up here. And please notice we have a contrast of 100. That's actually useful and important. Now I want to make it more complicated, so I'm going to go in and select second population, do the same thing. I'm going to set this to 8%, why not? This thing is, this one is 90, so I'll set this one here to be, let's say, 50. And that's probably okay. And calculate model. And then auto set axes. That's a little bit too much, so let me make this one 500. I'll recalculate and make it maybe 0.4. Okay, so now we have a Gini here, we have a beautiful dilute system here, and then we have this here. Let's go here and make this one a little bit smaller, so it's going to stand up a little bit more. Let's this one down. And I'm just looking for some pretty data which are going to be easy to fit. Okay, this looks, it's easier to fit than the previous one. It doesn't matter. Anyway, and this one has a contrast of 100, and this one is a contrast 100. Now, I have the model. I can go in and store in a folder. When I do that, it comes up with a dialog. I can store. However, because there's a model, it does not have where to store it. This model didn't come from any folder. So I can create a folder. I'll create a model to populations. Okay, continue. Now what we have now is in here we have a model to populations in a root folder. And inside that we have a calculated intensity and a scattering vector. And then we have radii. Oh, and I forgot. That's what I forgot. Let's make a change here just to make sure. Let's make it the diameters. And just delete these guys here. And then let's recalculate the model. And now it's all in diameters, because now this is a volume distribution diameters. Let's store it in a folder. Continue. To pop. Okay. So now I have a model to pop, I have an intensity, I have a Q vector, and I have diameters and a volume distribution. Okay. So now this would be these are the data here. By the way, I can display the size distribution here, and you can see how it looks like. Okay, so we have a one population here, then second population here. If you make it a log axis, they look pretty much like Gaussians, which is basically how the log normal looks like. Okay. So the next thing what we need is, in order to do any fitting in other tools, we have to give the other tools data. So I moved my arrow here, which points where my working folder is, into a root folder. And I'm going to type in here fits to populations. I can do that. Gonna need it. And that creates an empty folder which is called fits to two populations. Now I'm gonna copy that, and I need to I need to duplicate those things. So I'm gonna go in, I'm gonna select, copy down here, right click here, copy full path. That's the way to do. Duplicate, and I'm gonna call this one R model. So this is an intensity in that thing. So I'm duplicating this wave from whatever it is and putting it in here because my current working folder. I'm also going to call it S model. So I'm going to create two versions of it. That created both R and S. For now, they're the same thing. I'm going to copy full path here and say duplicate this, and that will be Q underbar model. Okay, so now I have a QRS. Unluckily, both of these have for now the same thing. So now what I need to do is I need to say S model, and now I'm going to multiply that by 0.05. That's going to make this wave 5% of its current values, which is a reasonably good estimate for errors in small angle scattering anyway. Okay, so now I have fake QRS data. These are QRS data. I can go in plotting. So I have a QRS data. It shows up here, and you can see those are the data I have in here. But except now Irena considers them to be QRS data. So the next step is, kill that too. Next step is let's try to fit it in size distribution. So we go in here. Here's a size distribution tool. Pick QRS, pick the data, and graph them. Perfect. We find them. Now you can see that the background accidentally, flat background is 0.1, so that would be a flat background here. We can go all the way somewhere above the background. This is way too long. We don't need that. We can add a 0 here. Now, this would have a contrast of 1. We used contrast of 100, so we give it a contrast of 100. Let's just give it a 2, for example, and do a fit. And you can see it fitted the data reasonably well. We're just going to set properly this sky background and squeeze it a little bit better and see if it fits the data. That fit it reasonably well. Let's see if we can do even better. Maybe even better. Well, okay. Oh yeah, we are missing a little part here. This is only going to 25, so let's give it 10. And let's try, oh, and let's give it more pins. Let's give it 300 pins and see what it does. Okay, now that looks even better. So now we can store it in data folder, just hit continue. So that's a result of this, and we can go in here and try to plot it just for the fun of it. Irena results. Now we have model 2 populations, and we pick diameters and volume distribution. So this is the original size distribution. Ignore how it looks. We'll fix that. Fits 2 population, and we fit another one here, and ignore that. And then let's go in and say we have a volume distribution, and let's give it a log x-axis. So if you look on this thing, you see that the original model, which is what we created, had this blue one, and you can see that it actually was terminated relatively early, around 30, because that's where the minimum size was 10, so it basically did not go all the way down. That's an interesting one. By the way, and then we have a distribution like this, and the size distribution sizes fitted something pretty similar, and up here in larger size it fitted that too. So that worked reasonably well. Now what we need to do next is we can go to unified fit and refit the same data with unified fit. So I'm going to pick the data, graph the data. Now I need to fit this with a one unified level, so I'm going to pick a unified level 1, and I have a guinea somewhere here. Check the 2 checkboxes, fit them, that's fine. We're going to come up here and say, and by the way, we know these are a sphere with a sharp interface, so we'll just fix the power law slope to 4 and fit that. Then we can also go in here and just directly type in here 0.1. And then we can go and select this area here, add a population number 2, fit there, okay, and then we can fit out here. Again, we don't have to fit the power law slope, we know it's 4. And then we can select the whole curve all the way from here to there, check all the checkboxes and say continue fitting. Okay, and we have fitted reasonably well. So that's another one. Now, what we need to know is that the P1 is 5% and that one's 4%. You're going to see in a second why. So if we go to Analyze Results, and just close this because we don't care about that, and then go to Size Distribution, we pick Level 1, and we pick Display. This is a volume fraction. So the unified fit cannot easily figure out the volume fraction. It knows an invariant, but doesn't know the contrast. So we're going to type in, this is 0.5, sorry, 0.05. And that's because that's this population 1, that's the smaller stuff. And this one, as I said, uses radii, and I can do a save on that. And this is population 1, and continue. Now I can go here and I want a level 2 display, and this level 2 had 4% volume fraction, so I'm going to go in and tell it it has a 4% volume fraction and do a save, call it pop2, and say continue. So now I have generated those. However, I can close all of that and all of that. So if you look inside this folder here, we now have sizes, volume distribution diameters, and a number distribution. And then we have unified fit, and the pop1 was the 0 version, and pop2 was this one here. The trouble we have is this is in radii and diameters. And so if I go in here and I do a plotting, and I go in and say I have these fits, and I pick the sizes diameter. So this was my sizes, and it's a volume distribution with log axes. Okay. However, if I now go in and pick the radii, this one, and add the data in there, everything's shifted. Okay, the green curve is shifted compared to the blue curve, and that's because this one's using diameter and this one's using radii, so it's a factor of 2. So what we now need to do is we now need to manually create a version which would be a scaled to diameter. To do that, I can basically go in and copy the data. So I can go copy, and I can do a duplicate. I'm going to duplicate this into diameter. Okay. Oh, and I have to be in the right place. So this red arrow has to point to the right folder, so these things can live in there this way. Okay, and now I can take this, which is a diameter, and make it twice the original size. So basically what this is, I can do it differently. I can do it this way, so it's more obvious what I'm doing is I can do this equals times 2. So I'm saying diameters are equal twice the radius. However, in that case, I need to also do another thing. I need to do a duplicate on this. And this one will now be a distribution with respect to diameter. And the problem is the area under the curve of the volume distribution is the volume. So if I made the diameters, or the x-axis twice as large, I need to make the volume distribution smaller. So I have to go in here and divide it by 2. So this thing goes and takes the original values and makes them half. Then I need to go and do the same thing for ones. So I'm going to duplicate number 1 into 1 here. I'm going to do the same thing for ones because that's my second population. Then I'm going to do this one. Oh, come on, that, 1 and 1, and I'm going to go here and duplicate this one. Okay, so now we should be able to plot all of them. So let's start with going in plotting again. So the very original size distribution which we have is actually inside the model 2 population. This is our model. This is what we started with. I'm going to add the data, make it into a volume distribution, and give it a log axis. Then I am going to go in the fits to populations, and in there we have the sizes, disk diameters, and we can add the data there and say ignore. And we can see that we are pretty much there with some misfit out here. Then unluckily, the newly created data we generated manually are not recognized as Irena results. If you look in here, you will see these are only the radii, because Irena knows what type of results it produces. But then we can do a manual insertion. So we just uncheck all of the boxes, pick the right folder, and then what we are looking for is for population 0, unified fit 0, and we're looking for the disk diameter 0, and out here we're looking volume distribution with 0. And then we are going to come in here and pick diameter 1 and diameter 1 and add the data. And so what you can see now is that, let's change graph details and use folders, use on the last folder, make the font size something really large. Oops, that's not very helpful. Use folders in legend. Okay, that is going to be better. And that's perfectly fine. So now if you look on what we did is we created these, we started with a size distribution in modeling package using spheres and a contour of 100. That's about here. And we got a size distribution for which we calculated the small angle scattering. When you fit it with the free flow size distribution, keep in mind that one does not care if it's log normal or which we used log normal or if it's any other one. It's just free flowing distribution. For the small particles, it's not too far, it's reasonably close, but it's, slightly off. But basically this qualifies as I'm fine. In the larger sizes, we fit them nearly perfectly. The larger sizes are a very good fit. The misfits are very small. And then what we used is we used this weird unified fit method. We fitted both the small and large sizes, so this is population 1, it's population 2. We gave the unified fit the proper volume fractions, which we used before. And then you can see that the unified fit has got the position right, it probably got the volume fraction, it had to get the volume fraction right. It's slightly narrower than what the original raw data were, but it's actually not too bad, and it's, the area under the curve is probably going to be it's going to be the same as we expected. And the fit to the larger particles is also pretty good and, fits reasonably well. So as you can see that you have 3 different tools, especially for larger particles, these different tools get basically the same results with some hand waving. There's some different approximations, some different mathematics. You go through completely different parts of the code, and eventually you reach the same results with all of these tools, or you fit the same size distributions, or sufficiently same that we can agree that these ones are in agreement together. So that's what I wanted to document, because sometimes I get a question which one of these tools I should use, and to a large degree it's a matter of preference. Obviously, if you have size distributions which are pretty much log normal or Gaussian, then the modeling package is better. If you have size distributions for which you don't know what the shape is, and especially when they're highly polydispersed, size distributions is better. And lots of times when you have a ugly polymer stuff with fractal systems, and inside it you have some nanoparticles which are whichever size distribution, then you can use the unified fit and fit the size and extract from the unified fit an approximate size distribution. So all of these options are open for you, and you can use them as you wish. And as you can see, 3 ways independently, you get the same results on this. So anyway, thanks for attention.